Alright, so in this video we go over section 3.5 graphing techniques and using transformations. Alright, before beginning this section, let's recall briefly what we did last time in the last video. So in the last video last week, we covered the different parent functions or parent graphs, like the graph of the parabola y equals x squared, the graph of the cubic function, the graph of the radical function. So in this case, these are the parent graphs. Now, what if we had a graph like this, like a parabola, however, shifted some units to the right or to the left, maybe up and down, or maybe having graphs that are wider or narrower, or maybe reflected or flipped upside down, so to speak. How are we going to describe those new graphs? We do that by means of transformations. So there are essentially three general kinds of transformations: shiftings, which are horizontal and vertical; compressions and stretches, which are both horizontal and vertical as well for each; and we have reflections about the x-axis and the y-axis. The reflection about the x-axis flips the graph upside down, while the reflection about the y-axis reflects flips the graph about the y-axis, or flips it horizontally rather. Okay, like reverses the order of the graph. So we're gonna go over pretty much the simplest case: vertical and horizontal shifts. So we discuss in this definition the vertical shift. So we suppose we have some function, which that function can be anything like f of x equals x squared, f of x equals x cubed, the square root of x, whatever function, and consider k some positive number. So to graph y equals f of x plus k, all we do is add k to the y coordinates of the points on the graph of f. Otherwise, if k is negative, subtract k units to all the y coordinates of the points of the graph of f. So in this case, this shifts down k units, and in the previous case shifts up by k units. We're gonna do one example right here. We're gonna do this by hand, and then we're gonna verify this using our graphing calculator. Alright, so let's graph f of x equals x squared. So f of x equals x squared, the parent graph contains the point, the origin, the point 1, 1, negative 1, 1. And then when x equals 2, 2 squared equals 4, negative 2, x equals 4. And when 3, that's going to be 9. And when negative 3, it's also positive 9. So I'm going to use blue for this graph. Alright, now on the same graph, and then in this case I'm going to use green. Okay, let me box this with blue. Let me box this with green. And this with red. We're going to use three colors for the three different functions that we are going to graph. Okay, so this plus 3 indicates that I should add 3 units to all the y coordinates. For example, this point right here, adding 3 units, it's going to shift 1, 2, 3 units up. So I'm gonna have this origin and shift it 3 units up. The point 1, 1, I'm gonna add 1 to the y's. I'm gonna add 3 rather, so I'm gonna move it 1, 2, 3. Same this point, I'm gonna move it up 3 units. Then I'm gonna focus on this point, which I'm gonna add 3 units to the vertical component, 3 more units to the vertical component or the y coordinate. Then these 2 points again, I'm gonna move them shifted rather 3 units. And I'm going to have this graph right here. Okay, so we have a parabola shifted 3 units up. I'm going to do the same, but now for h of x equals x squared minus 4, every single key point, 1, 2, 3, 4, 5, 6, 7 points, I'm going to shift them down 4 units. So this origin, I'm going to move it 1, 2, 3, 4 units. And then another 4, 1, 2, 3, 4 units for the point 1, comma 1. For the point negative 1, comma 1, I'm going to go 1, 2, 3, 4 units. The point negative 2, comma 4, I'm going to shift it 1, 2, 3, 4 units down. The point 2, comma 4, I'm going to shift it down 1, 2, 3, 4 units down. The point 3, comma 9, I'm going to shift it down 4 units, 1, 2, 3, 4. And then same by symmetry here. So in this case, okay, let's graph. We don't have to go all the way up. This way is fine, just like this is fine. Okay, now let's verify this using the graphing calculator. So I'm gonna go to, so let me turn on the calculator, and then what am I gonna do? I'm gonna go to Y. I'm gonna click Y. I already have it set to match the colors with what I did by hand. So I'm gonna have x squared, x to the second, and then x to the second plus 3, and then oops, no, not over here, not this plus 3. Let me delete plus 3, and then x squared minus 4, and then we're gonna click graph. So that's our original graph, the parent graph of x squared, and then the green one, well, it doesn't look green over here, so maybe if I put it here, and then the red one, which looks 4 units down. All right, so here you have the comparison between what we do by hand and then what we do using our graphing calculator. So now let's look at another transformation here. So now let's look at horizontal shifts. Okay, so now we are going to have some f of x plus h and f of x plus h and f of x minus h. In this case, we are going to shift the x's, not to y's, and it's going to yield into a horizontal shift. Okay, and in this case, as opposed to the previous case, the plus k, we added k units to the y values, and the minus k, we subtracted k units to the y values. Now, for the f of x plus h, we subtract h from the x's this time. And for x minus h, we add h to the x coordinates. So let's see. Let's look at an example here. So again, let me label this with blue, or box it with blue, and then I'm going to box this with green, just so we can represent all the 3 different colors. Okay, and in this case, I'm not going to graph too many points. Well, maybe I will, never mind. So again, I'm going to have the origin 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4, and then 3, 9, and then negative 3, positive 9. And let me draw the parabola that is represented by connecting these dots. Okay, now for the green one, this plus 3 right here indicates that I should subtract 3 to the x coordinates. In other words, this origin, I'm going to shift it 1, 2, 3 units to the left. This negative 1, 1, I'm going to shift it 1, 2, 3 units to the left. this 1, 1, I'm going to shift it 1, 2, 3 units to the left. And then this 1, 2, 4, I'm going to shift it 1, 2, 3 units to the left. This negative 2, 4, I'm going to shift it 1, 2, 3, 3 units to the left, and these 2 points as well. 1, 2, 3, and then 1, 2, 3. And then draw the resulting graph. And we're going to have the parabola shifted 3 units to the left. Now for the red one, I'm going to do the same, but in this case, this -5, as described in the box above, we add h units to the x coordinates. Okay, so the x coordinates, in other words, we add 5. I'm going to shift this 1, 2, 3, 4, 5. And then this one is 1, 2, 3, 4, 5. This point is going to go 1, 2, 3, 4, 5. And then this point is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. One more. 1, 2, 3, 4, 5. So we have this now. Okay, so we have this labeled by colors. Now I'm going to do this in the graphing calculator just to show you how do we do this. So let's start it up first, and then I'm going to go to the Y, and then I'm going to clear this one, and I'm going to clear that one. So I'm going to open parentheses, and I will type x plus 3, close parentheses, and square. And then I'm going to open parentheses, x minus 5, close parentheses, and square. And look at the graphs we're going to obtain. Again, we get the parent graph in blue, and then the green one shifted 3 units to the left, and then the red one, which is shifted 5 units to the right. Okay, let's look at another case. Reflections. So for reflection, so again the same, we have a function f, and then we are going to have a negative sign outside of the function, or multiplying the function, and the negative sign multiplying the x's only. So the first case reflects the graph across the x-axis. In other words, draw it upside down. Or flips. Okay, which this is how we typically, we say it in plain English rather than in the mathematical or academic vocabulary, right? So that's how we typically do it. But the correct way is reflect across the x-axis. On the other hand, we call it, I guess, flips, but in the reverse or backwards. Okay, backwards. All right, so in this case, it's a reflection about or across the y-axis. So in this case, for the first one, you can think of the x-axis as a mirror. So when you have a negative in the front, you will see the same graph on the other side of the mirror. And on the second case, we're going to use the y-axis as our mirror, and then we are going to have the graph mirror on the other side of the y-axis. So let's do an example. As usual, I'm going to, this is going to be blue, this is going to be green, and this is going to be the red one. Okay, so square root of x. So in this case, I'm not going to use the graph of f of x equals x squared. I'm going to use a different one this time. I'm going to use the graph of the square root of x, which in this case, let's recall how does that look like. So you might want to just take these points, the points that have points whose x values have a perfect square root. Of course, you can take any point, but to make our lives easier, we choose points that have perfect square. Right? It's not like polynomials in this case that we can just plug in our favorite number. In this case, well, yes, our favorite numbers for the square root of x functions are numbers, are x values that have a perfect square root. So in this case, with blue, okay, so if x equals 0, the square root of 0 is 0. If x equals 1, the square root of 1 is 1. If x equals 2, well, it's not a nice number. I'm going to go to the next perfect square. And in this case, 4 is the square root of 4 equals 4. Wait a minute, 2, not 4, 2. And then the next perfect square is 9. So the square root of 9 is 3. And I'm going to draw this graph, this kind of curve. If you look at this function, it's like 1/2 of the side of the parabola that we had over here in the previous example. And we're gonna look more about this later in the semester, how this is in a way the inverse function to x to that of f of x equals x squared under certain condition. But well, it's a little bit too early to talk about this. This is just something that we are going to be connecting in later in the semester. All right, let's focus on the green graph. Notice the negative sign. It's outside, in front of the function, just like over here in the generic form, in the general form. What is this going to do? Reflect the graph of y equals f of x across the x-axis by multiplying the y coordinates by -1. So in this case, what am I going to do? With green, so I'm going to have the points 0, 0, 1, 1, 4, 2, and 9, 3. I'm going to focus only on the y values, and I'm going to multiply this by -1 times -1 times -1 times -1. So that will result, well, in this case 0, 0, 1, -1, 4, -2, and 9, -3. So I'm going to plot these points 0, 0, and then I'm going to have 1, -1, and then 4, -2, and then 9, -3. So in this case, what do we have? We have the graph upside down, flipped, as we described it here in the math, if you will, mathematical slang. Okay, now let's look at the other reflection. I'm going to write these values again, these points 0, 0, 1, 1, 4, 2, 9, 3. And every single, in this case, I'm going to have, notice the position of the negative sign. It's inside of the function. It's affecting the x's this time. So this time I'm going to multiply all the x's by -1. And I'm going to obtain the following order pairs. Well, 0, 0 still, -1, 1, -4, 2, and -9, 3. And I'm going to plot this point, the point 0, 0, the point -1, 1, the point -4, 2, and the point -9, 3. And now I'm going to have a graph that, if you look at this, it meets the description. Okay, reflects the graph across the y-axis. So this is the y-axis. This is the mirror. We have the same graph on the other side, as opposed to the other case. The x-axis was the mirror. All right, let's do this in the graphing calculator to verify these results. It's always a good idea to verify this, and then I'm gonna clear, then I'm gonna go second square root of x, and then negative second square root of x, where it's x, or x, and then I'm gonna delete everything else. And then I'm gonna have, let me clear, second square root of negative x. Keep in mind that when typing these negative signs, the calculator has two different signs. This is to subtract. This is not the one I'm using. The one that I'm using is this one in parentheses. This is the good one. This one is the one I use here, because if you put the other negative sign, you're gonna get an error. Okay, so let's see. Let's click on graph. In blue we have the parent graph, and then we have that one in green and the other one in red, exactly as what we did by hand. Alright, so we're done with reflections. Let's look at another case. Okay, so now we are going to look at compressions and stretches. So we're going to have vertical scalings. So for vertical scalings, we are going to have functions that have, similar to the previous one, with some number instead of a sign. So let me highlight this one with, or rather box it with green, to graph y equals a times f of x, and with green to graph y 1 over a times f of x. So what are we going to do? So in this case, well, when a, it's a number greater than 1, okay, could even be a fraction. Okay, we said that the graph it's undergone a vertical stretching, which typically we call it expansion or dilation, okay, by a factor of a. In order to, in the numerical point of view, what do? It's multiply all the y coordinates by the quantity a. When we have something like 1 over a, where a goes from between between a and 1, that is, a is a fraction, that's 1 over a. For example, 1/2, 1/4, 1/3, 3/7, a number that lies between 0 and 1. To make it easy, I had it like this. So in this case, what do? So in this case, when we have a fraction between 0 and 1, the graph will have a vertical shrinking or compression or contraction by a factor of 1 over a. To graph this, we divide all the coordinates by the fraction 1 over a. Or if this is not 1 in the numerator, but it's still a number that lies between 0 and 1. So in this case, I'm saying something more in general, like 1/2, 1/3, 1/9, 1/17, right? But we could have numbers that are like 3/7, or what else? I don't know, 11 over 12, for example, and or I don't know, maybe 3/4 or 7/8. But in all these numbers still meet this condition. They are between 0 and 1. Okay, that's what we want. And in that case, so we divide, and in that case what we do is still multiply by these fractions. Again, notice I use the word divide, but that's when we have some 1 over another a. So we just divide by a, or simply multiply by 1 over a. So let's look at a couple of examples. So in this case, I'm going to use the example of for square root of x, 2 times the square root of x, and 1/2 the square root of x. Okay, so well, this graph is going to be a little bit bigger this time, and I'm gonna go like 0, 0, the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. Okay, so what am I going to do? Okay, first of all, let me write down these order pairs. So the order pair 0, 0, 1, 1, 4, 2, 9, 3. And all these points for the graph of 2 times the square root of x, we are going to multiply all the y coordinates by a. So in this case, a is 2, so this one times 2, times 2, times 2, and times 2. So what am I going to get here? I'm going to get the following points. Well, 0, 0, 1, 2, 4, 4, and 9, 6. So let me plot those points. So 0, 0 still. 1, 2. And then 4, 4, and 9, 6. And I'm going to draw these points together and connect these points. Okay, oops, I didn't graph the other, which looks like this. Now, what do we have for the third one? 1/2. So this time I'm going to multiply by, in this case, everything, all the y values by 1/2. So I'm going to have the same points again. 0, 0, 1, 1, 4, 2, 9, 3. And I'm going to multiply these y's by 1/2 times 1/2 times 1/2 times 1/2. Only the y values. And what am I going to obtain? 0, 0, 1, 1/2, 4, 2 times 1/2 is 1, and 3/2 is simply 3/2. For your convenience, you might want to use 0.5 over here and 1.5. Either way is fine. Now let's plot these points. 0, 0, 1, 1/2. Notice half is somewhere here. And 4, 1, and 9, 1 to 3/2, which is 1.5. So what did we get here? In this case, we got a shrinking, as stated over here, vertical shrinking versus vertical stretching for the green one, right? For the green one became bigger, the red one became smaller in terms of its compression, right? So now let's do this again using the graphing calculator. So let me go to y equals. So in this case, I'm going to replace this with a 2 root of x, and then I'm going to second insert 1/2, and I'm going to get rid of the x. So let's graph. So there's a parent graph first, the stretched and the compressed. There it is. All right, let's look at another case. The next, and I believe that's the last case of scaling. Is it? Yes, that's the last case. And it's going to be a little bit similar, but in this case in the reverse way for horizontal scaling. So again, we're going to have some function f, but in this case, instead of a, we're going to have b. Now, look at the position of that factor that is going to compress or stretch. Is now inside of the function, not multiplying the function. And in this case, it does the reverse. So when we have a fraction, we multiply by b. Otherwise, if we multiply by a big number, by a number greater than 1, we divide by b as opposed to the previous case. So this time I'm going to take a different function. I'm going to take the absolute value function, okay, which is the one that looks like a v. It's the v-shaped function that we looked last time. I'm going to take this point. It's like having two linear functions, two identity functions, one in the positive direction, the other one in the negative direction. So let's go ahead and graph a few points on that graph. So with blue, the origin 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. 1, 2, 3, 4, 5. And then I'm going to just draw the graph. Okay. All right. So that's the graph. The graph in blue will represent this absolute value of f of x, absolute value of 2x. Okay, 2x. So what are we going to do here? It's the second case. Well, by the way, this should have been the green one, not the red one. So in this case, all the x coordinates, not the y coordinates. Notice in the previous case, we multiply the y coordinates. Now we're going to do the same thing, but pretty much, but with the x coordinates. So I'm going to have the points, not all the points, by the way. I'm going to choose just some key points. The point, of course, the origin, 0, 0. I'm going to choose the even points, negative 2, 2, and 2, 2, and negative 4, 4, and 4, 4. I'm going to choose 5 points this time. I'm going to take the time to do a few more points so you can see the difference between all of them. So what are we going to do? Divide the x coordinates by, in this case, 2. So divide by 2, divide by 2, divide by 2, divide by 2, divide by 2. Okay, only the x values. So 0 over 2, well, it's still a 0. Negative 2 over 2, that's a negative 1. The y remains the same. Negative 2 over 2, that's positive 1. I mean, positive 2 over 2, that's 1. And 2 remains the same. Negative 4 over 2, it's a negative 2, 4. And then 4 divided by 2, that's 2, 4. So we are going to plot these points. The points, again, the 0, 0, negative 1, 2, and then 1, 2, and then negative 2, 4, and then 2, 4. And now, yes, there is a connection between this and the previous case. In this case, we had a graph that was kind of vertically stretches, but in this case we're looking at horizontal shrinking. So horizontal shrinking, compression or contraction. So look how this graph got contracted or compressed, shrinked. Now let's look at the graph in red, the one that is going to correspond in red. So I'm going to write these points again. 0, 0, negative 2, 2, 2, 2, negative 4, 4, 4, 4. Okay, and then so I'm going to multiply, in this case, I'm going to multiply all x coordinates by, in this case, 2. Times 2, times 2, times 2. Times 2, times 2. Okay. So, what are we going to get here? So 0 times 2, that's still 0. Negative 4 comma 2, 4 comma 2, negative 8 comma 4, and I'm not gonna have space for these 2 points, but still we are gonna get a good picture over here. So this is going to be 4, or rather 8 comma 4. Okay, I'm gonna try to plot at least a few points. So the origin, of course, and then negative 4 comma 2, and then 4 comma 2. And I wish I had enough space here to show you the rest, but in this case there's not enough space. And notice how this graph goes stretched horizontally. Now let's verify this using the graphing calculator. So I'm going to go back to y, but in this case I'm going to use the absolute value operator to reach that one. By the way, we go math and then click to the right to reach the num menu and the first one, which is going to be the apps, and then type X. Okay, then I'm going to go to the second. Let me clear, and that's going to be, again, I'm going to open absolute value bars by clicking math. I'm going to scroll one to the right to get to the num, and I'm going to click enter because the one it's already highlighted, which is the one I want, and that's going to be 2x. And the same, I'm just going to go a little bit faster here. Math num apps 1 over 2x, and let's see what do we get. Okay, so that's the original graph in blue. And then there goes the next one, the green one, which is shrink, and the red one, which is stretched. All right. So this covers pretty much everything about, these transformations and all about the different ways we can shift a function. So now we're going to put all this together into context. So we are going to have some examples in which we are going to apply more than one transformation. So first I will retrieve some files here, and let's see. All right. So we're gonna have the following. So we're gonna start with the graph of a parent with the function, some parent function f of x equals the absolute value of x. What are we going to do? Shift left 2 units. All right. So in this case, So I created and you may find this in the last page of this handout, that I'm working on the video. The last page has this sort of a cheat sheet, if you will, okay, which I'm gonna put here so we can rely on this for the rest of the section. So in this case, we want to shift this function to the left. Okay, so in this case, it's a horizontal shift. So shifting to the left, again, subtract goes to the left, add goes to the right, but again, it goes in the opposite sign. So in this case, to shift to the left, what am I going to do here is y equals absolute value of x plus 2. And then I'm going to shift up 3 units. Now it's going to be, well, up and down means vertical shifting in this case. Plus is add or up. Minus is subtract or down. So I'm going to add, I'm going to have the same. How many units? 3 units. Okay. Now, we are going to reflect about the y-axis. So, in this case, absolute value, x plus 2 plus 3. Okay, I need a negative sign somewhere, but where are we going to do? So in this case, let's look at reflections. So when we multiply the y coordinate by -1, that is, if we put a negative in the very front or in front of the entire function, what happens here is this flips the graph upside down. So that's not reflection about the y-axis. So in this case, we want to have a negative multiplying the x. That's going to shift the, not shift, reflect all the points across the x-axis, the y-axis rather, which in this case, by multiplying the x coordinates by -1. And those are the functions that we obtain here. All right, so let's see. Graphing functions doing more than one transformation, not like the ones we did in the first examples in which we went one transformation at a time with only one operation at a time. Now we are going to combine this. So in this case, we are going to graph the function starting with the graph of the basic function. So in this case, the basic function is, suppose you don't have these 2. Suppose you don't have this -4. Suppose you don't have this +3. You have the function f of x equals x squared, which I'm going to graph here. I'm going to use this grid here, 0, 0, the origin, 1, 1, -1, 1, 2, 4, 3, 9, and 4, 16. I'm gonna go all the way to 16 and then -2, 4, -3, 9, and then -4, positive 16. So I'm going to go and draw the graph of this parabola with these essential points. Okay. And then I'm going to select maybe, I'm going to select 5 points. Okay. So I'm going to select 5 points, 1, 2, 3, 4, 5, well, actually 7 points. The points that are, that's going to be, I'm going to go -3, 9, and then -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, 3, 9. Okay, so all these points. So the first transformation, we start with the x's first, which in this case, well, here is like a quick summary of what we do. We take care of horizontal shifts first, and then any reflections. In this case, first we do reflections, if any, and then compressions and stretches, and we do at the end these vertical shifts. So in this case, the first transformation, which is x minus 4, what are we going to do? Minus h, add h to the x coordinates. So we are going to add 4 to all x coordinates. Okay, and we are going to obtain new points. 4 minus 3, which is 1, 9. 2 minus 4, which is 2, 4. 4 minus 1, which is 3, 1 remain. The y values remain the same. And then 0 plus 4, that's 4, 0. And then 4 plus 1, that's 5, 1. And 8, no, not 8, that's actually 6. 6, 4, and 7, 9. Okay. Now the next transformation, so compression, in this case we don't have any reflections because we don't see any negative signs multiplying the x's or in front of the function. So we're going to go to the next, which is compression and stretch. And in this case we have vertical stretch because in this case we're going to have this a vertical scaling right here, which is some number a to multiply the y coordinates by a. So 2 times 9, that's 8. Times 2, and then times 2, times 2, times 2, times 2, only the y value. So the x values are going to remain the same. So 18, well, I'm not going to have space to graph that point. So 2, 4, 2, 8. And then 3, 2, 4, 0. 0 times 2 is 0. And then 5, 2 plus 1, that's 3. 6, 4 plus 4 times 2, oh wait a minute, not 3, that's 2, we're multiplying, and 4 times 2, that's 8, and 18, another 18, 7, 18. And then finally we are going to look at this plus 3, and that plus 3 is going to describe a vertical shift adding k to the y coordinates of each point. So in this case we are going to add 3 to all the y values. Okay? So we are going to have the following. 1, 18 plus 3, that's, well, this one is not even going to be possible to graph, so I'm just going to cross it. And then I'm going to cross this one as well, the first and the last. I'm going to focus on the 1, 2, 3, 4, 5 points. So I'm going to have 2, 11, 3, 5, 4, 3, 5, 5, 6, 11, and that's going to be about it. So I'm going to plot these new points. I'm going to use green in this case. Let me box them with green. All right, it looks like I chose too many points in this case. In the next examples, I'm not going to choose too many points. So I'm gonna plot the point 2, 11, and then 3, 5, and then 4, 3, 5, 5, and 6 comma 11. As you can see, we have a new parabola. We have a new parabola. Now let's describe these transformations in words. So we have x squared shifted 4 units to the right, and then 3 units up. Notice in this case I skipped the or. When describing this in words, you don't have to follow the same order. That's fine. And then what is this? Vertically scaled by a factor of 2. Some of the homework questions will give you some exercise like this, and they will give you some multiple choice questions in which you will be expected to choose between the correct answer. So, and in this case, they will be described like this in words or something similar. Now let's verify this using the graphing calculator. Why not? Okay. So let me clear. So I'm going to start with the parent graph, x squared, and then 2 times parentheses x minus 4, close parentheses, square, and then, what was that? Plus 3. Okay, and let's hit graph. Do you see anything different than what we did? Maybe the difference here, of course, my graphs are not perfect. I'm not really good at drawing. That's number one. And the other difference between what I did on the paper and what we have on the screen is the aspect ratio of the calculator. In this case, I don't know the aspect ratio, but this is not a square screen. This is a perfectly square grid as opposed to what we have on the graphing calculator. So that's why it might look a little bit different. My graphs are going to look a little bit more smashed as opposed to those on the graphing calculator. All right, so let's look at another example. Oh, before looking at the other example, you might want to click second graph to reach the table, and you will see all these points as pairs. For example, the point 2 comma 11, 3 comma 5, 4 comma 3, 5 comma 5, 6, 11, 7 and 21, etc., which is what we have gotten if we added the 3. 18 plus 3, 18 plus 3, that's 21. Of course, you can always look at the table of values, but the reason why I went step by step, just to show you how all these transformations work on the behind the scenes of looking at this table or looking at a graph like this. It is very important to have an understanding of what the mechanic is behind all these transformations, which is by doing the corresponding operations as described in this cheat sheet, if you will, which is not really a cheat sheet. It's a summary of all the transformations. All right, let's look at another example. Let's look at the example f of x equals 3 over x minus 2 plus 1. All right, let's identify first the parent graph. So suppose we don't have the 3 in the numerator. Suppose you don't have this minus 2. Suppose you don't have that plus 1. So here the parent graph is, the parent function is f of x equals 1 over x, which is the reciprocal function, the function that we had in the previous section over here. All right. And I'm going to use, in this case, I'm going to use 3 different points. The point -1, 1, the point 1, 1, and the point 1/2, comma 2. Okay, I'm going to use those 2 points to graph the function. So let's see. In this case, 1, 1, -1, -1, and then 1/2, comma 2. And I'm going to do this. I'm going to do the graph, the parent graph, which is going to look like this. All right. So that's a point 1, comma 1. And notice something interesting here. This graph has a horizontal asymptote, which is the x-axis, and a vertical asymptote, which is the y-axis. Okay. Now I'm going to choose these 3 points again. The point -1, comma -1, the point 1, comma 1 to make it easier, and the point 1/2, comma 1, or comma 2 rather. Okay. So I'm going to do one. I'm going to do one at a time. I'm going to do first what I'm going to do. I'm going to do the horizontal shifting, this -2. Okay, let's look again at the horizontal shift. So to the x coordinates, I'm going to add h. In this case, I'm going to add 2 to the x coordinates. So +2, +2, and +2. So far, so good. All right. Now, so 2 minus 1, we are going to obtain. That's going to be 1, comma -1, 3, comma 1, and what else are we going to do? 2 plus 1/2, that's going to be 5/2, comma 2. Now, in this case, we are going to have the vertical asymptote x equals 2. Actually, x equals to 0. And this vertical asymptote will be shifted. We are going to have y equals 0 as our vertical asymptote. Okay, wait a minute. X equals 0 is the vertical asymptote, and let me call it VA for vertical asymptote, and HA for the horizontal asymptote. So in this case, the vertical asymptote, which corresponds to x, I will also shift it by adding 2 units, and that's going to become x equals to 2, and the horizontal asymptote remains the same. Let me look at the next transformation. In this case, the vertical, in this case, stretching. So in this case, for the vertical stretching, let's see what do we do. Let's look. Vertical scaling, multiply by an integer a, multiply the y coordinates by a. So I'm going to multiply times 3, times 3, and times 3. And in this case, we are going to multiply the number which describes the horizontal asymptote by 3. But in this case, 0 times 3 is just going to be 0. So I'm going to have 1, -3, 3, comma 3, and 5/2, comma 6. X equals 2, which is the vertical asymptote, remains the same, and y equals 0 times 3 remains 0. And then I'm going to do one last transformation, which is this +1. In other words, this looks a lot like the plus k, which is adding k units to the y coordinate. So I'm going to add 1 to the y coordinates, all right, to get never mind, to get this shifted up 1 unit, okay? But in this case, the horizontal asymptote gets added at 1 unit again. So in this case, we're going to obtain the following points: 1 comma negative 2, 3 comma 4, 5 halves comma 7, and the vertical asymptote remains x equals 2 and the horizontal asymptote remains 1. Becomes 1. Okay, so I will use green for these new values. Actually, you might want to rewrite this 0.5 halves as 2.5 to make your life easier. 2.57. Okay, so in this case, unfortunately, I'm not gonna have space to have that point drawn. So, but well, I will figure something out for this. So I'm gonna have the asymptote, the horizontal asymptote shifted 1 unit up. Okay, and the vertical asymptote shifted 2 units to the right. So in this case, I'm gonna have the point 3 comma 4, this one right here, and then the point, what was the other point? 1 negative 2. Okay, and then I had the point 2.5 comma 7, which is somewhere here. Well, I'm just gonna draw this graph like this, and this graph like that. Okay, it's a little bit hard to see the difference here, but if you focus on the colors, the parent graph is 1 over x, and then the shifted one is the one with green. Let's do it in the graphing calculator. And here is where the calculator and what we do in paper differs by quite a bit. I will show you why. So 1 over x, oops, I can quit. 1 over x, oops, and then clear 3 divided by open parentheses x minus, was that a minus? Yes, x minus 2, close parentheses, and then add 1 plus 1. So if we graph, so that's our parent graph, and then that's our shifted graph. So what's the problem here? Yes, the calculator is a really smart device. However, it's not that smart, and the reason for that is because the graphing calculator is not going to draw these horizontal and vertical asymptotes for you. So in this case, it's very important that you know all the aspects of parent graph before understanding how the shiftings are going to go, especially like this graph right here, that on top of very common points, we're going to have also horizontal asymptote and a vertical asymptote, and those also suffer changes. Those also get shifted by k and h units depending on the case. Okay, all right, so let's see, what are we going to do next? Let's look at another example in which we're going to get this function right here. All right, so let's see. So we have f of x equals 1 minus the square root of x. This is going to be a little bit tricky. We need to pay attention with the order again. Okay, so suppose we don't have that 1, we don't have the negative, we don't have that positive 2. So what are we going to have? This is going to be each parent graph is going to be f of x equals the square root of x. Okay, whose points are 0, 0, 1, 1, 4, 3. 4, 2. Okay, those are the main points for this function. All right, so now I'm not going to do this by the point. In this case, what am I going to do is I'm going to go with the transformation. So in this case, the first thing we do, I'm going to go by replacing, so from f of x, we go by replace x with negative x. So I'm going to have f of x equals the square root of negative x. And then the next instruction is look at this point right here. So in this case, I'm going to replace, or rather, yes, replace x with x minus 1. But be careful because with this negative sign. Negative, so x becomes x minus 1. That is how we are going to obtain this 1 minus x, because when we distribute this, all right, when we distribute this negative sign, we are going to obtain that. So if you want to rewrite this function from the very beginning, f of x equals the square root, I'm going to factor out the negative, that's going to be x minus 1. And this way is way easier to see the transformations that we do inside of the radical. And finally, we need the final touch, which is at 2. For vertical shift. Okay, and that's going to give us f of x equals negative x minus 1 plus 2. So I'm going to fix this by distributing this negative, and I'm going to have f of x equals 1 minus x plus 2, which matches our original graph. So now I'm going to do the same on the graphing calculator here. So I'm going to go clear, clear, and this is going to be f square root of x, and then the square root of 1 minus x, and outside a plus 2. Let's see how the graph of this looks like. Okay, so I'm just going to go second table this time, and I'm going to look for cool values. So at this point, we already have a good understanding of how the shiftings go. So in this case, I'm just going to take the values, the ones in black right here, and which is the x's, and then the green ones, which is for the green graph. So it's going to be 1, 2, and then 0, 1, 2, 0, 3, and then negative 3, 4, Do we have anything else? Well, in this case, all the way to -8, 5. But in this case, we're not going to have enough graph. So I'm just going to do this way. Okay. Now, if you want to see like stage by stage, okay, let me show you the textbook over here. Hopefully I can find the page real quick so you can see all this described in a better way. So let me find the page. So this will be, it's right here. That's actually the function we just did, is the example on the book. So the first step, well, is to start with the parent graph. If we were to do the first transformation, which is at the 1, so in this case I did it the reverse way. They did it the other way by adding the 1 first and then changing the reflection, and then did the 2. So in this case, shift everything 1 unit to the right, then reflect everything with respect to the y-axis, and then shift everything 2 units up. Okay, now something we didn't do with the examples with these examples here, because they're gonna ask you to do that, is to find the domain and the range of the function. So in this case, the domain and the range of the function that we get shifted here. Okay, so in this case, well, the domain, it's not going to change. It's going to go domain. It's going to be -infinity to +infinity, or in set notation, x belongs to the set of all real numbers. X such that x belongs to the set of all real numbers. And the range is not going to go all the real numbers. If you look at the range, the lowest point in the y values is 4. And using that in set notation, x, or rather y, such that y is greater than or equal to 4. All right. Let's look at the domain of the other function, the one in green. Well, in this case, everything is fine until we get to this vertical asymptote, which is located at x equals 2. Okay, so this will be dictated by this. So those are the values that the function does not take. So domain, in this case, well, -infinity, but it doesn't take the value of 2. So we exclude it this way. Or using set notation, x such that x cannot be 2. For the range, if we scan the graph from bottom to top, it's going to go really nice until we reach the y value of 1, which we cannot take. And then from 1 again all the way up to +infinity, which in set notation it's going to be y such that y cannot be 1. Okay, cannot be 2, cannot be 1, because those are the locations of the asymptotes for this graph. Now, for this third example, okay, in this case again you might want to use the trick to break this up into the 2 directions. So in this case, scan the graph from left to right to get the domain, which in this case it goes from -infinity to +1, including the 1, because we have solid point. We don't have an open bubble to exclude it, which in set notation x such that x is less than or equal positive 1. For the range of the function, we're going to scan the graph from bottom to top, and in this case we find that the lowest value of y is 2, and it goes all the way up to positive infinity, which in set notation y such that y is greater than or equal to 2. So those are going to be also questions from the homework. Do the transformations, do all the shiftings, and then do find the domain and range. But I mean, typically it's better to get the shifted graph first and from there get the domain and the range. Right? We're going to do other kinds of examples in which we are going to basically expand this concept. So under which situations, how far can we go with this shifting? So we're going to have some very interesting questions, examples. So we have this graph of some function. We don't care about the algebraic definition. This is going to be like y equals negative 2, y equals x, and then whatever this is. But we don't care about that. What we care is the key points. The key points that I'm going to point out here, negative 4, comma 2, and then negative 2, comma negative 2, actually negative 2. And then the point 2 comma 2 and the point 4 comma negative 2. Those are the points that we are going to shift to obtain new graphs. All right, so we're going to use this first graph which contains contains 1, 2, 3, 4 interesting points, 4 key points, and we're going to do these shiftings again. Okay, it would be a good idea if I do it the old way. Negative 4, negative 2, I'm going to write them. Negative 2, negative 2, 2, 2, 4, negative 2. Okay, so let's look at all the, let's have our summary here. So in this case, this plus k, we're going to add k units to the y coordinates to get the new points. So add 3 to the to the y coordinates. Sorry about that. Add 3 to get new points. So the new points we are going to obtain here are going to be negative 4, still the same. 3 minus 2, that's a 1. Negative 2, comma 1 also, and 2, comma 5. And 3 minus 2, that's also 1. 4, comma 1. So I'm going to plot these points again. I'm going to plot these points rather in this Cartesian plane that we got, and I'm going to connect the graph. So in this case, all we did is get this graph and move it up 3 units. That's ultimately what we did. So negative 4 comma 1, negative 2 comma 1, 2 comma 5, and 4 comma 1. So we're gonna have this. Okay, do you see the difference between these two graphs? Negative 1, it was just shifted 3 units up. Let's see what happens with big G of x, f of x plus 2. Let's refer to the shiftings, and I'm going to write down the points. So negative 4 comma negative 2, negative 2, negative 2, 2, 2, and 4, negative 2. So every single point, what are we going to do with x plus 2? So x plus 8, subtract h to the x coordinate. So in this case, minus 2, minus 2, minus 2, and minus 2 to obtain the following points: negative 6, negative 2, negative 4, negative 2, 0, 2, 2, negative 2. All right. So we're going to have the points negative 6 comma negative 2, and then negative 4 comma negative 2, 0 comma 0 comma 2, and 2 comma negative 2. So basically the same graph as the one that we have. Wait a minute, it is 0, 2, not negative 2 comma 2. So this graph didn't get shrink or compressed. It was only shifted to the left by 2 units. Now, what are we going to do with the next graph? So we are going to have a p of x equals to negative f of x. So let's refer to the reflections. To do that, we are going to multiply the y coordinate by negative 1. That it's this one right here. So let me write down those points: negative 4, negative 2, and then negative 2, negative 2, 2, 2, 4, negative 2, and let's see. Multiply the y coordinate by negative 1, so times negative 1, negative 1, times negative 1, times negative 1. Okay, so we are going to obtain points in which the x's remain the same, and we multiply negative 2 times negative 1, that's positive 2. Essentially, change the signs of the y coordinates. And we are going to plot these points. Okay, so let's see. Negative 4, comma, positive 2. Negative 2, comma 2. 2, negative 2, and 4, comma 2. So all we got is a graph now that is upside down. Okay, let's see. Let's move on to the next example, to the next part of the page. So now we're going to do 2 transformations at a time. All right, so we are going to have, rather than doing 1 row at a time, this time I'm going to do the 2 operations. In this case, it's going to be easy to do all that. So I'm going to have the points again. Let me write them down. It's going to be negative 4, negative 2, negative 2, negative 2, 2, 2, 4, negative 2. So in this case, referring to the transformation, so we are going to have horizontal shift, which will have an impact on the x's, which in this case, we're going to subtract h units. That is, we are going to subtract 1 to all the x's. And then this minus 2, it looks like minus k. Subtract k units to the y coordinates. That is, subtract 2. And let's do these operations together. All right, so negative 4 minus 1, that's a negative 5, and then negative 4. Negative 2 minus 2 is negative 4. Negative 2 minus 1, that's going to be negative 3. Negative 2 minus 2, that's negative 4. Okay. And then 2 minus 1, that's going to be 1. 2 minus 2, that's going to be 0. And then 4 minus 1, that's going to be 3. And negative 2 minus 2, that's going to give us negative 4. So this is what we are going to obtain. All right, let's plot these points on the Cartesian plane that we have here. So -5, -4, -3, -4, 1, 0, and 3, -4. So we have this graph right here. So it's essentially the same shape. We moved it 1 to the left and 2 down units. All right, let me write down the points again. -4, -2, -2, -2, 2, 2, 4, -2. Let's refer to the shiftings here. Okay, let's refer to this. So in this case, look at big cube x 1/2, which looks like a scale. It looks like a scaling in this case. So 1 over a f of x, in this case we divide by a, or multiply all, rather the y coordinates, we multiply them by a. So let's see. So times 1/2 times 1/2 times 1/2 times 1/2, which is the same again as divide by 2. Multiplying by a half is the same as multiply by 2. Either way, however you prefer to show this work, either way should be fine. Now let's see. So the x's remain the same. -2 times a half is -1. Okay. -2 remains the same. -2 times a half is -1. And then 2 times a half is +1. And 4 remains the same. And -2 times a half is -1. So let's plot these 4 points in here. So -4, -1, -2, -1, and then 2, 1, and 4, -1. So now we have something a little bit different this time, right? We have it a little bit shrank. The graph shrank because of this 1/2. So the graph shrank or compressed vertically by a factor of a half. Now let's look at the next transformation. So let's look at f of -x, which is to multiply the x coordinates by -1. So in this case, we are going to have a reversed graph. So first of all, -4, -1, -4, -2, and then -2, -2, 2, 2, 4, -2. So in this case, multiply the x coordinate by -1. So I'm gonna have 4, -2, 2, -2, -2, 2, and -4, -2. So let's plot these few points in this Cartesian plane. So I'm gonna go for -2, okay, for -2, and then 2, -2, and then -2, +2, and -4, -2. So essentially, it looks like the original graph almost, except that is reversed. So look at the original graph, it just got reversed. Let's look at the next shifting, next and last shifting. So f of 2x. So we're gonna look at the horizontal scaling in this case. So we are going to divide the y coordinates by b again. B, a number inside of the parentheses multiplying the x, we do the opposite, divide y coordinates by b. So same points, negative 4, negative 4, negative 2, negative 2, negative 2, 2, 2, 4, negative 2. Okay, so what are we going to do? Okay, divide the y coordinates by 2. So it's going to look very similar to something that we already have. Okay. Wait a minute, not the y coordinates. This should be the x coordinates, in fact. So I'm afraid there's a little typo here. This should be an x. I'm glad I saw this typo on this cheat sheet, because in this case we're talking about horizontal scaling, which doesn't make sense to change a y coordinate. It's an x. I'm glad I just realized about it. So I'm going to divide by b, or multiply by a half. Either way, I'm going to divide by 2. So I'm going to have negative 4 times 2, that's negative 2, negative 2. Negative 2 divided by 2, that's a negative 1, negative 2. 2 divided by 2, that's a 1, 2, and 4 divided by 2, that's going to be a 2, negative 2. So we're going to have negative 2, comma, negative 2. Negative 1, comma, negative 2. 1, comma, 2, and 2, comma, negative 2. What happened here? Oops. What happened here? Well, the graph shrank horizontally, so we had a horizontal scaling in here. Okay, so this exercise summarizes all possible shiftings one way or another, but in a different type of exercise, in which we are not given some function f of x. We are given the graph, and all we do is select key points and do all the operations on those points as dictated by or established by the different shiftings here, by this summary here. All right, let's see what's next. Let's get more let's see, some more applications to these shiftings. All right, in which we are going to be given x-intercepts of some graph. Okay, so in this case, we have the x-intercepts that are, again, well, in this case they're giving us the numbers, but our job here is to write this as ordered pairs. In this case, the ordered pair for the first x-intercept is -8, and then 1, 0. Those are the points. What are the x-intercept of the graph of y equals f of x plus 4? Again, let's refer to our transformations here, to our summary. So in this case, we have plus 4 plus h plus h. So we're going to subtract h units to the x coordinates. So -4 and -4. So the new intercepts are -12, 0 and -3, 0. So those are the new x-intercepts. So in this case, horizontal shiftings affect the x-intercepts of a given graph. Of course, because it's a horizontal shift, which has to do with x values. What about in this case? So in this case, it's going to be very similar, -8, 0, 1, 0. So f of x minus 3, what are we going to get here? Okay, so basically the same, but in this case add h units. In this case we are going to add 3. To not the y values, for some reason I wrote them underneath the y value. So in this case we are going to obtain new x-intercepts, which are going to be negative 5 comma 0 and 4 comma 0. Those are the new x-intercepts. Alright, so what about when we have some constant multiplying the function? Okay, so in this case we have something of the form y equals a f of x, which in this case a is 2. Multiply the y coordinates by a. So in this case we are going to multiply the y's times 2. But in this case, this is not going to have any effect, because 2 times 0 is still 0. We're not doing anything to the x's. The only thing we're doing is to the y, so this remains the same. Now, let's look at the next transformation. What are the x-intercepts of the graph of y equals f of negative x? So we start with the given points. And in this case, what is this telling us to do essentially? Well, so when we have f of negative x, multiply the x coordinates by negative 1. So in this case, these are going to shift sides, to switch sides of the side of the Cartesian plane. So this is going to go 8 comma 0 and negative 1 comma 0. Okay. All right, suppose a point, okay, negative 3 comma 5 is some point. I think we already did a little bit of this. However, we are going to do more combinations that we haven't done before. So let's warm up with this negative 3 comma 5 to be some point of the graph of y equals g of x. Okay, so what is the point on the graph of g of x plus 1 minus 3? So again, this plus 1, it's going to ask to subtract h, or to subtract 1 to the x coordinate. So subtract 1 to the x coordinate, and this minus 3 is to subtract 3 to the y coordinate. So this will become negative 4 and 3. Okay. So let's see. Let's see what's next. Negative 4 comma. Actually, no. This is gonna be a 2. I did the wrong math. Never mind. Okay. What about the next one? All right. So the first thing we do, I'm gonna do one at a time here. I'm gonna do negative 3 comma 5, and in this case what I'm gonna do first is the shifting with the negative. For this x minus 4 is asking us to add h units, in other words add 4 units to the x coordinate. So add 4 to obtain the point 1 comma, what is this, 1 comma 5. And then let me look first at the multiplication by 3, that is a vertical scaling. So in this case, we're going to multiply the y coordinate by 3. That's going to give us 1, 15. And then look at this negative sign. This negative, it's going to, in front of it, it's going to ask us to multiply the y coordinate by -1, which in this case is times -1. That's going to give us 1, -15. And finally, we have this plus 3, which is no other than adding k units to the y value, which in this case I'm going to add 3 units. That is going to give us 1, -12, which is final answer to this. We in this case notice the sequence we follow one at a time. All right. So let's see what comes next. So we're going to have again the same point, -3, 5. Oops. -3, 5. So in this case, we're going to have some 3x plus 9. We haven't done something like this in the previous example. So what is this 9 going to do? So in this case, the 9 is going to shift the plus 9 is going to shift, or asking us to subtract 9 to the x coordinate, to the x value, to the x coordinate. Okay, subtract h, which is 9, to the x coordinate. And that's going to give us -12, 5. Let's do the next transformation. This, the 3 multiplying the x. Now let's look at the very last horizontal scaling. In fact, we are going to divide the x coordinate by b. In this case, the x coordinate, we divide that by 3 to give us -4, 5. Let's look at the next and last page. So now we're going to have a very interesting problem I made up here. It's not, this type of problem is neither on the textbook nor is on the homework or anything, but potentially I could ask you something like this on the quiz. All right, so again, this is going to wrap up again all these transformations and shiftings and changes to a given function. So in this case, we have some function, whatever it is. We don't care what the function is. What we care is that the domain goes from -5 to 7, and the range goes from 11 to 19. The question is, what is the domain of and range of -f of -x? Interesting. Okay, keep in mind that whatever we see in the inside of the parentheses has to do with the x's. Whatever we see outside, either multiplying f or adding a number outside, has to do with the y's strictly. All right? That's basically the main takeaway of this section. Whatever inside the parentheses, the or the radical or something like that, shifts the x's. Everything else, multiplying outside, adding outside, or dividing outside, shifts the y values. All right, so let's see what's going to happen here. So let's take care of the x's. So the domain, x belonging to the set of point -5, 7. So this -x, multiply the x coordinates by -1. So I'm going to multiply everything by -1. -1 times -1 times -1. Okay, this will become it's going to become +5 and -7. But there's something weird about this. We need to fix this. Because when we write domains of functions, when we use interval notation, notice this is interval notation. This is the interval of numbers comprised from -5 to +7 inclusive. We always write this from the smaller to the larger, the smallest to largest. But in this case, this doesn't make sense. We need, this is not the right way to write it. This is mathematical baloney. This doesn't make sense. We go and write it down as x belongs from -7 to +5. That makes sense now. Now let's look at the range. Y, which belongs from 11 to 19. Right? So, looking at the shifting summary here, the negative in front of the f shifts, or rather multiply the y coordinates by -1. We do exactly the same. Times -1 times -1. So that's going to give us y belonging to -11 to -19. But again, this is not the right way to write it. This is not right. Just the same way this was not right, we go with the correct order. The correct order is then y -19 to -11. Because -19 is smaller than -11. So we go with the correct order. So this is the new domain and this is the new range. Alright. Let's look at something, well, something easier, something less weird as what we did here. So f of x -7 and +6. So the -7 is going to affect the domain, the x's, and the +6 is going to affect the range, the y's only. So let's see. I'm going to write x belongs to -5, 7, and y belongs to 11, 19. Okay, reviewing the shiftings again. Here we have the following. So the -7 looks a lot like adding 7 to the x coordinate. So add 7. And for the y's, the +6, the plus k, looks like the very first form, which is also adding k, which is in this case add 6 and add 6. So the new domain will become x belongs to the set of numbers between 7 minus 5, which is 2, and 7 plus 7, which is 14. And same for the y's. So the range goes from 11 plus 6, which is 17, and 19 plus 6, which is 25. So those are the new domain, the new range. Let's look at something more involved. Holy moly. All right. So for the domain, for this function, let's see. Let me start writing the domain which x belongs to -5 to 7, and the range 11 over 19. 11, 19, not over. Okay. again, this is going to affect the x's right here. And this -3 and the +6 is going to affect the y. So I'm going to do this separately. Okay, first of all, what is this +4 suggesting to do? So the +4 plus h is to subtract h to the x coordinate. So all the x's I'm going to subtract 4. And that's going to yield the following: x belonging to, so the new domain is going to be -9, 3. What is this 1/5 telling us? Ignore the negative. These are two different transformations. This is going to be some shrinking or expanding, and this negative is going to be a reflection. So I'm gonna do I'm gonna do that first. So in this case, the 1/5, okay, it's the second to the last. Multiply the x coordinates by b. In this case, b is 5, if you will, so I'm going to times this by 5. So x belongs to, okay, -45 and to 15. And then what about the next transformation for x? So the next transformation for x, we are going to multiply the x's by -1. Okay, so times -1 times -1. So I'm going to get the following: x belongs to positive 45, comma, -15. But again, this doesn't make sense because this is not how we read intervals. We need to -15, the lower first, and then the upper. Actually, this x, I'm going to turn this into something like this, and then something like that. And that's the new domain. Now let's do the range. Let's look at the y's. First of all, these 3. I'm going to do these 3 first. I'm going to multiply each y and 3 by 3 to give us 33 and 19 times 3, which is 57. Then I'm going to do this -1. Okay, this times by -1, which will give me y belongs to -33 to -57. But again, this doesn't make sense. When it comes to reflecting, again, we always have to change the order of this. -57, -33. Right, so that's what I'm doing. Writing them in the correct order. Finally, what do we do? This +6, according to our vertical shifts, add k to the y coordinate. So add 6, add 6. So y belongs to -57 plus 6, that's -51, and -33 plus 6, that's -27. All right. The next one, it's going to be a little bit similar. So So let's see. Let's look at the domain, which is x belongs to -5 to 7, and the y's, which are going to go from 11 to 19. Okay, so I'm going to rather subtract 5. Right, this because this is what we do. This plus h subtract h plus 5 subtract 5. So this is going to give us x going from -10 to +2. And then we have this 2x or ax. Rather bx divide by b. So 2x divided by 2. So x belongs to this is going to be -5 to 1. And that is the new domain. What about the range? So for the range, okay, this is what we did for the domain. This is what we do, the 1/4 and the -5. So for the y's, times 1/4 times 1/4 to both of them. So that's going to give us y belonging to 11/4. Well, in this case, we're going to keep it as 11/4 and 19/4. And finally, this -5. It's telling us to subtract k because it's minus k, subtract 5 because it's -5. So in this case, 11/4 -5, if you use a graphing calculator, you should get -9/4. And 19/4 -5, if you use a graphing calculator, you should get 1/4. Let's verify that again, just to make sure. So 11/4 -5, math frac command, that's negative -9/4. And then in this case, 19/4 -5, that's a -1/4. Okay, so this last example wraps up this section. Again, this is one of those problems that I decided to make myself. So hopefully this puts everything together, and now you can have you can see the bigger picture of what this is. Okay, so this is the end of this video of this section. I'll see you on the next one.